How do intelligent systems store knowledge and turn it into decisions? The answer lies in knowledge representation and reasoning, two core principles that support understanding and problem-solving in artificial intelligence. In this explainer, you will follow the main methods, reasoning styles, challenges, and practical uses described in this topic. Knowledge representation is the method used to encode knowledge about the world in a format an artificial intelligence system can use. Its purpose is to support reasoning and problem-solving. In simple terms, it turns information into a machine-readable form that a system can work with. A useful representation needs three key qualities. It should be expressive enough to capture diverse and complex knowledge. It should be efficient enough for quick retrieval and reasoning, and scalable enough to handle large datasets effectively. Knowledge representation provides a foundation for reasoning, decision-making, and learning in artificial intelligence systems. The material also distinguishes between declarative knowledge, which covers facts and information, and procedural knowledge, which describes how to perform a task or follow steps. Logical representation uses formal logic to express facts and relationships. The examples given include propositional logic and predicate logic. This method is suited to statements such as all humans are mortal, where rules and relationships can be written in a formal, structured way. Semantic networks represent knowledge as graph-based structures. In this method, nodes stand for concepts or objects, while edges show relationships between them. The material links semantic networks to concept mapping and to understanding relationships in areas such as language processing and recommendation systems. Frame-based representation uses structured templates for stereotypical situations. A frame can include slots for attributes and values, such as make, model, and color for a car. Scripts extend this idea by representing sequences of events, like ordering, eating, and paying in a restaurant. Production rules express knowledge through if-then statements. They are described as a way to represent procedural knowledge and are widely used in expert systems for diagnostics and problem-solving. A simple example is the rule that if it rains, then carry an umbrella. Ontologies organize concepts and relationships into formal hierarchies. Description logics support this by representing concepts, roles, and individuals in a formal way. The material highlights their use in semantic reasoning and ontology building, including subclass relations such as a dog being a mammal. Reasoning in artificial intelligence is the process of deriving logical conclusions from available knowledge. Once knowledge has been represented, reasoning is what allows a system to draw outcomes from it. The topic introduces several forms of reasoning that serve different kinds of problems and evidence. 0203, 0405. Deductive reasoning moves from general facts to specific conclusions. Inductive reasoning moves from specific observations to broader rules. Abductive reasoning searches for the best explanation of observed facts, while probabilistic reasoning uses probabilities to manage uncertainty, with Bayesian networks given as an example. Monotonic reasoning follows the idea that once a conclusion is reached, adding more information does not invalidate it. It is based on classical logic, assumes complete and stable knowledge, and follows strict deductive rules. The material places it in settings such as proofs, database queries, and traditional expert systems. Non-monotonic reasoning allows conclusions to be revised when new information appears. It is designed for incomplete, changing, or uncertain knowledge and adds flexibility when evidence shifts. The material mentions default logic and circumscription and uses the flying bird and penguin example to show revision in action. Data-driven reasoning starts from known data and applies inference rules to reach conclusions. In forward chaining, a system begins with initial facts and derives new facts step by step until a goal is reached. The material links this approach to expert systems and predictive analytics, used in expert analytics. Goal-driven reasoning starts with a goal and works backward to find the facts or rules that support it. In backward chaining, the system identifies what is needed to achieve the target and reasons in reverse. This approach is linked to troubleshooting systems and automated planning. 04 is the next phase in our discussion. 05 follows closely, expanding on these concepts. The topic gives 2 case studies. In medical diagnosis systems, forward chaining uses patient symptoms as data and applies rules to suggest diagnoses and treatments, with MyKin named as an example. In automated planning systems, backward chaining helps robotics plan steps toward objectives such as pick and place tasks. Several broad challenges appear across knowledge, representation, and reasoning. Ambiguity makes it hard to represent knowledge with multiple meanings. Inconsistency creates conflict inside the knowledge base. Uncertainty limits, confidence in conclusions, and scalability becomes harder as knowledge bases grow. Reasoning under uncertainty means making decisions or drawing conclusions when information is incomplete, ambiguous, or probabilistic. The material highlights ambiguity in data, incomplete information, the probabilistic nature of events, and the added computational complexity that comes with advanced probabilistic models. Forward chaining and backward chaining are also presented as ways to address uncertainty. Medical diagnosis systems may use patient symptoms to predict diseases with associated probabilities, while automated planning systems may account for obstacles and delays. Bayesian networks are named as a probabilistic model used for such reasoning. The development section combines probabilistic reasoning, Bayesian networks, and linear algebra. Bayesian networks are described as directed acyclic graphs, whose nodes represent variables and whose edges show dependencies or causal relationships. Belief propagation updates probabilities based on evidence, and linear algebra supports the matrix operations involved. These ideas support several practical applications. Expert systems use production rules for medical diagnosis or financial analysis. Natural language processing uses semantic networks and ontologies. Autonomous vehicles use probabilistic reasoning for navigation and decision-making, and recommendation systems represent preferences and relationships to suggest products or services. Intelligent systems depend on strong knowledge representation and careful reasoning to work with complex information. You have seen the main representation methods, the major reasoning styles, the role of uncertainty, and key applications. Together, these principles help artificial intelligence systems interpret information, solve problems, and adapt to new situations.